Hello, everyone. So, a schema is all you need, and maybe also some sleep. But first of all, I want to thank you, organizers of this awesome conference. I'm Mattia Manzati. I'm a developer. I like to break stuff. I like to call undefined and access properties of undefined. And, well, as you may know, it's not my first time here in React Alicante. You may remember me from previous call of last year, like durable workflows of an introduction to effect. And this year, we're going to speak about schemas. So, I do not need to convince you that types are great. Maybe we took a few years to realize that, but thanks to tools like TypeScript that brought a type system into JavaScript, finally we were able to step up our code bases and finally build production-grade applications in JavaScript. And well, it's not a mystery that the more those typings are well-written and strict, the more our code base became robust. And we can develop our entire application based on some assumption of our data is defined. But well, unfortunately, that's not it. Because unfortunately, we eventually have to reach a point where our application have to reach for the outside world. And now our application types cannot be strict anymore. Our application has to reach for our outside data, and as soon as we do that, all of those assumptions goes away. And this is not restricted like speaking about network APIs. If you think about it, this applies as well when you have to fetch some data from the storage. Even if you manage yourself the data from the storage, what does tell you that that data hasn't been corrupted? Or maybe you pushed a new application update that now is unable to read from that data. Well, and this is a very common problem, and a lot of libraries exist out there to solve this problem. And this problem is solved by data validation libraries that, given any unknown data that may come from the wire or the storage, what they do is that they perform validation and ensure that the shape of the incoming data is exactly the one we expect. They are basically doing type checking at runtime. And sure, those libraries are an additional dependency, but, well, they are definitely worth it because they make our application less prone to failures due to malformed inputs. So let's say that you decide to use one of those libraries, like, for example, Dot. And now your code base will look something like this. You will use the library to define how your structure is shaped, and then you'll notice that now, instead of relying on the TypeScript types, you will usually infer those from the runtime definition. And well, that is expected because if we remember, TypeScript types get compiled away. So we still need something at runtime to perform the actual data validation. And so now, let's say that you have used Thought, you have validated your incoming API data, and now what happens? Well, it seems odd enough, but most of the time, when you fetch something from the storage in memory, you now present it to the UI, and then now the UI updates that in-memory representation, but eventually you have to persist it back. So, well, we would like to have something that performs encoding back. But unfortunately, that is out of scope for data validation libraries because they only focus on input data validation. So unfortunately, we need to write additional code that, given our data, produces back something that is in the shape of the encoded data by our storage. And now the resulting code isn't much cleaner and smaller as before, but, well, it works. So should we bother about it? Well, to be honest, we should care about it. If we are reading data from the storage, updating, encoding it back, and sending that back, we need to ensure that that implementation of the encode function is correct. And this seemed trivial, but we basically had it a cost of manually defining that function that performs basically the same way of validation the other way around. And this function is actually one critical point of your application. If you do this function wrong, you basically incur in potential data loss for your application. Did you notice that in the slide before we had a bug? We called toString instead of calling toJSON. And what would have been happen is that while users were editing the data in the application, they were corrupting data in the storage. So that's definitely not great, not something you want to push into production. So, well, one way to be sure that we successfully implemented in code and we don't push something broke into production is something called property-based testing, where instead of testing a specific function with a specific value, we instead describe the properties that we expect from the encode function. And well, the property we expect is actually pretty easy. We expect that given any random to-do, we can encode that random to-do, and then from the encoded value, we decoded it back, and then in the end, we expect that the decoded value is exactly the same that we had initially. We are basically doing a round trip with the same value without changing it, and we expect that doing the deserialization round trip, we get back the same value. Well, but now we are basically stuck in a loop, you know, because in order to ensure that we are doing encoding correctly, we need information about, again, how is structured our data, because our fast check library needs information about how it is structured to produce random values. So, well, I think this is kind of a mess. It's a recursion problem, you know. So maybe there is a better way to solve this problem rather than repeating ourselves 3, 4 more times, because, you know, there are also many other related problems. So let's go back to the drawing board, okay? We had this initial TypeScript definition, okay? And if we think about it, the problem here is that we are using different solutions, we are considering different problems, but they are all related to our data definition. So why are we using different things when we are dealing with only one thing, our data definition? Maybe we should instead move to something that starts from our data definition and derive everything out of that. Well, it would be kind of awesome to be able to directly use TypeScript types and inspect those in order to get the values and create whatever you want, but unfortunately we can't, they get removed. So we need to construct artificially some values like an object or whatever that represents our JavaScript type. And the problem here becomes how we can find a good encoding that is able to represent all the possible types that a user can construct. Well, finding a good model for that may seem very hard, but maybe the solution has always been just under our nose. Well, our applications are built in JavaScript, right? So our objective is being able to fully describe a JavaScript type with a runtime value. So maybe we can just use something that's really similar to TypeScript AST to describe our structure. Maybe not exactly TypeScript AST, but because that has additional information about source code location and whatever, but we can take a very good inspiration from that. And now that we have started with this kind of definition that seems very similar to the AST, what we can do then is then construct functions that traverse that AST and then construct the function we want. For example, we start with the definition before, we create a function that takes the AST, construct a decode function, and then we have our decode function. Well, this is exactly the implementation details that makes, in my opinion, fschema the best solution for defining and using schemas in effect. fschema, instead of focusing on a particular problem about data like validation, it provides you with the APIs to define a schema and interpreters that will allow you to create decoding, encoding, arbitrariness, and many more, starting all from your JSON from your AST definition. And FSchema has been written by Giulio Canti, which is an amazing guy that have already worked in the past on libraries focused on data decoding and encoding. You may already have heard of things like FPTS, TCOMP, or IOTS. Well, FSchema can be considered kind of the successor of those libraries. Well, let's start with a pretty simple example. Okay, so the first thing that we should do is import everything as schema from, guess what? Effect schema. Now that we have imported the effect schema, the first thing we can do is describe something. Guess what we are going to describe today? Something very new that no one has ever done. We describe how is define a to-do. A to-do is a struct that has an ID, and I'll go for a numeric ID, and then we'll have a name, and that name will be a string. And maybe we will want to know if it is completed. Dot Boolean. Okay, and now that we have defined our schema, as you can see, the APIs are very, very, very simple. We can do exactly like with other tools. We can extract the type by saying type to do equals schema.schema.type, and we pass in the type of our to do. And that way, instead of having the description of the structure, we finally have the actual implementation of the interface. So that can be used in our API. For example, we can say log do. One takes it, takes a to-do, and give it to-do, console.log, and we'll do to-do dot something. Okay, and as you can see, they are fully typed. Great. Well, so the list of combinators there are out there are enormous. I don't want to spend much time about that, but there are all the basic types you can have, plus something that is not strictly a type of TypeScript. You can have something like saying, I want a name that is not an empty string, so non-empty string. Or you can say that the ID should be indeed a number, but maybe you want a positive number. And so you may say, okay, this looks pretty familiar to any other solution. What's the difference? Well, let's try to console.log our to-do. And let's see what we have here. Well, we don't have much here. The only interesting thing we have here is our AST. And if we try to run this, you will see that it will log exactly something like we have in TypeScript. Okay? So what happens is that those APIs just construct an object. And that's really great because this produces really light APIs that can be easily tree-shaken and are very, very, very composable. But now that we have this structure, how do we create a validator function from this structure? Well, this is actually very easy. What we do is we just do parse to do equals, we call an interpreter. And the interpreter is schema.decode unknown sync. And now these interpreters want as parameters the schema. So the schema is the to-do schema we just defined. And now you can see that we get back exactly the function we are looking for. Now we can test it and say const result equals parse to do. And we gave it an ID, one, name by milk, and is completed, false. Okay. We console.log the result and run the example. Okay, you can see that we have successfully logged the value, but what happens is, for example, we pass an invalid value. We have left an empty name. Well, we get an error thrown. Well, let's see this error. Well, this error says, this is the structure we expected. At the name field, we expected an empty string, but that refinement failed because we get actually an empty string. And this error can be also customized by using what's called annotations, because fh schema AST also includes annotations that can be used by the interpreters to change their behaviors. So we can, for example, annotate the entire object and say that we want to identify this structure as a to-do. Now, if we try to run again the example, we can see that now the error will say to-do instead of all that gibberish thing. And I am sure that if you are one of the OCaml guy, you are really happy to see exception thrown. So if you don't like exception, forget what I just said before. There is also another interpreter that instead of throwing exception, what we'll do is return an either data structure. So you can do the code unknown either. We pass again our structure, and now we see that the resulting function has changed. Now it returns an either. And what is an either? Well, an either is just a structure that has a tag, and we can see result dot tag if the tag is left. That means that we had a failure, so we can console.error, that failure we had, result dot left, and we have the message of the failure, else we succeeded, and then we can log the error. But now the value is inside the right. Okay, so success. Now, if we attempt to run again this thing, you can see that we had an error. So we went into the error path. We can fix this. And if we run again, now we have success. And now you can create exception-free applications. But, well, by default, the decode method returns only the first error you have. Maybe you will have more than one error. Maybe the name is empty, and you passed in something wrong as is completed. If we run that, we will see that we return just the first error. But if you are into forms, for example, you may want all the errors, because you want to throw those at the user and let the user fix it. So how can you get all of those errors? Well, it's really simple. You pass in an option to the interpreter saying that you want all the errors. And now, when I run again, you'll see that the interpreter will also return all the errors you have. So we have seen how we can decode a value that comes from the wire and successfully get back our type. So what about the other way around? Well, most libraries, as we have said before, don't allow that. Well, with fx schema, it's just calling another interpreter. You have your schema definition, and now you have an interpreter that, given a valid value, produces back the encoded structure as unknown. But, well, as unknown, maybe unknown is not useful where you are encoding back data. Because if we remember the graph we had before, after you change the data in your UI, then you call an API with that data. And maybe you have TypeScript typings for that API, so you know the specific shape of that. And well, that's why fx schema has a second type parameter. That's called the encoded type. Let's see it in action. Let's go back to our example. Let's say that we have also a date field. For example, create a date that will record when it has been created. Okay, so now we can see that our type is of kind date. But well, how do we serialize the date over the wire? Well, definitely it's not a JSON primitive. So how can we do that? Well, if we take a closer look, the documentation says that this specific schema tries to convert a string into a date object. So if we try to extract the encoded schema, so the version that we expect to persist or receive over the wire, by using its encoded type utility, we pass again our to do, we'll see that in this type, our created at is a string. And that's expected. As JSON, we will pass the JSON string. And now that we have seen that we have those two data types, we can fully describe all the operation that Schema is able to perform at runtime. Schema can take in an unknown value, and that given that unknown value, thanks to its internal AST, it can first check that that unknown value is the input encoded we expect. Let's take the data example. Given an unknown value, it will first assert that that value is a string, and after it has asserted that it's a string, it will perform the decode operation that converts a string into a date. But it will also allow, if you already know that you have for sure a string on hand, to decode from a string directly to a date. And, as we have seen, vice versa. And it also allows for other interesting operations, like asserting that the data you have on hand is exactly the one you expect to have. And well, Schema is not actually just limited to perform sync validation. Thanks to its interop with fact, Schema can actually perform also async validation. And that's really, really, really interesting. Let's take a look at a simple example. Let's say that we want to do something crazy. Let's say that we now want to ensure that this entire structure dot filter effect. This filter effect will basically add a check on the whole structure. We'll receive the data structure. And now we can perform async stuff like effect.gen, function. We can create an arbitrary delay, something like console.log, starting validation. We can sleep for 2 seconds. And then return true. OK, so here we have added an asynchronous validation. OK? Now, if we try to run that again, we'll see that we will get some failures. Let's see, maybe with the sync variant. Encode the code unknown sync. OK. And I don't need this anymore. OK. You'll see that we have a few failures. OK. We need to fix those. We need to say that it's completed is false. And we need to provide it by milk. OK, but created at is missing, yeah. That's the fun of like coding. OK. Yep, let's just take that away so we can make it simpler. OK, we see that now we get an error saying this schema cannot be resolved synchronously. Yeah, that's expected. We used asynchronous validation. So what we need now to do is tell the use, instead of the sync interpreter, the promise one. Now, instead of getting a result, we will get a promise. And now we can do something like result.then console.log completed. if we run again our example, we'll see that it'll start validation, it takes a while, and then it completed. Schema supports also asynchronous validation. And well, Schema is not really only just about encoding and decoding, as we said before. With Schema, we can also, for example, derive arbitraries. What are arbitraries? Arbitraries are basically random values that can be used. We mentioned that before, that we can use, for example, arbitraries to perform validation on our encoded function implementation. So let's start, obviously, by importing the arbitrary interpreter. Arbitrary from, guess what? fs schema arbitrary. And our arbitrary implementation relies on fast check. So we can import fast check. Okay, so now we have our schema definition. Let's maybe get rid of the async validation example. Okay, and now we need to create an arbitrary. Imagine how do you do that? You just call the interpreter. So arbitrary to do equals arbitrary dot make, and we pass in our to do. And now we can see that we get back a fast check arbitrary. And that fast check arbitrary can be used to generate random to-dos. We call fast check dot sample. We pass in the arbitrary we just created, and we tell the number of random to-dos we want. Let's say that we want 5 values. If we console.log those random values, let's see what happens. Here you can see that you have 5 random to-dos, all for free, just based on your schema definition. And who doesn't like free stuff? And well, you can also imagine that the more your schema definition are true and strict, let's say, for example, maybe the ID is an integer, not something like a number, you can see that they become more and more and more real and like something that the user may have created. So they can become something that maybe you can use in your API to return mock data. And you can also imagine that you can build other things from a schema. Maybe we can also get a JSON schema. I mean, who doesn't like free stuff? So imagine that now that you have your mocked APIs, maybe someone comes and say, can you also give me an open API spec for those? Well, maybe you can generate automatically the JSON definitions, JSON schema definition for the instructions involved in your API. Well, and doing that is actually pretty easy. Guess how you can do that? You just import another interpreter, and that's the whole talk. No, sorry, I'm just kidding. What you can do here is now create your JSON schema as JSON schema dot make, and you pass in your to-do. And you get back a JSON schema. Maybe we can also log it to see it better. We'll also make it prettier. JSON stringify, JSON schema, null, and I like two, because most of people do use two. And you can see here that we get for free our JSON schema definition. But, well, don't you like this description? Isn't funny? Well, this is definitely something you cannot ship. So how can we change this description? Well, again, you can just use annotations. So we can say, for example, that the name field, we want to annotate that with a title of the job that needs to be done. And now, if we try to run again, we'll see that now the name field has a title, the job that needs to be done. And that all comes from Schema's AST with its annotations. And what else? Well, Schema has already a lot of built-in interpreters, and the list keeps going. You can have decoding, you can have encoding, as we have seen. We can assert, arbitraries, JSON schema, equivalence, or pretty-print. And schema can be used for various applications. You can, for example, create a RPC server that use fh schema to validate the incoming request, serialize the data that's coming out, and also create JSON schema that can be used by third parties, and also use JSON schema to create an hash of the signature of the contract to ensure that both the client of the RPC and the server are speaking the same version of the contract. Or we can create HTTP API using the OPM API definition generated from schema. Or maybe you can generate static TypeScript typings from your schema. And well, schemas are something that I predict that, in my opinion, will also become more and more important because AI training can be supported by schemas. Thanks to schemas, we can tell our AIs what data we expect to get back, and we can also put constraints and validation on the data we expect back. So, what happens if something is not in the list? Well, you can write yourself an interpreter. Let's try, for example, to write a very simple interpreter that will just take a to-do and say that if that to-do is equal to another. Well, let's start by making our definition more simpler. We can have a name, we can have a string, and we can have a Boolean. Okay. Let's say that this is our definition. And we want to create something that, given the schema AST, produces a function that compares two values and says if they are the same. So we need to traverse our AST. So let's create a function that will traverse our AST. The AST can be imported from import everything as AST from fh schema AST. Okay, so this is an AST, and this will create a function that, given A unknown and B unknown, will tell if those are equal. Boolean. Okay. 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 Sorry. Well, you know. What happens when you live code? Everything breaks. Okay, so ast.ast. Okay, what you need to do is very simple. You switch around your AST definition and say case. This is ast.tag. Okay, I'm not able. In case this is, for example, a number. Okay, we want to return a comparison that between A and B just does A equals B. Okay, and the same can go for other things like case Boolean or case string. Okay, but if we have something more complex like type literal, which is the struct we have defined before, we need to do something a little different. We should do something like return. We have A and B that are our values, and then we loop to the property signatures that we have in our schema, and we say for each property signature, for each property signature, we will check basically that A at that property signature dot name is equal to B at that property signature dot name, which is basically the same as calling again the interpreter with the property signature type we have at that type and passing in as values that and that. Okay, so in case something has not been managed by this interpreter, we can just throw ist.tag. So now let's try to use it. Now let's say that I want const equal. I assure that I am almost finished. Const equal equals go of our to-do dot ast, and we should get back this kind of signature. I won't spend time here defining that, but if we do something like id1 name a and id1 name a and console.log that. Okay. Now everything won't work. Okay, we got true, true, true. That's fine. If we change, that's because I map it here, but I need, instead of saying map, I need to say every. If every of those check passes, then it's true. If we change something, drum roll please, it's false. So we successfully written our first schema interpreter. Okay, so we have just seen that the limit is just your imagination. So please go there, go out, and happy scheming. Thanks for your time.